Okay, this is lesson 3.2b. We're talking about least squares regression line. So what is that? It minimizes the sum of the squared residuals. So I'll show you a picture of that, and then I want you to kind of experience on your calculator. So for this one, do you see each of those red points? Those are actual data values. We know that the line, we learned that the line of regression is a prediction line, and the distance, the vertical distance between each of those points and the regression line is called the residual. If it goes up like that, it's positive. If it's going down to a point, that's a negative residual. If you see those thicker lines there as part of that square, if you make a square out of each one of those residuals, so you literally take each residual and just say, I'm going to make a square of that size of the residual, that's what the squared residuals are. They're visual, like an area almost there. So, and so you want the least squares regression line is making the sum of those areas of those squares as small as possible, right? So let's try this. So you might already have this data typed in from the other day, but if you don't, go to listen spreadsheet page, call one sprint, call one long, and type in the data. Then hit the home key, go to data statistics page, and choose your X variable, which is sprint. It's our explanatory variable, and then our long is our response variable. It looks like it has a negative association, moderately strong, maybe, I'm not sure. But so and it's linear. Okay, so we're going to do a linear regression. So when you do that, actually, we're going to not do a regression yet. Let's wait on that. Analyze, add movable lines. We're going to try it on movable lines. So you can kind of grab this line. If you hover over it, hit Control Center click and grab it, you'll be able to move the line. You want to grab it on the ends more right now to start with. So if you kind of grab the ends and move it until you're kind of happy with where the line is. I tried to just put it, I don't know, in the center-ish for this one. If you want to show the R squared value, which is, well, let's R squared value, if you go to settings, click diagnose, oh, it does have that. So this doesn't have an R squared value because it's not a line of regression, I guess. But it does show this. So if you go menu analyze and go to residuals, it will show residual squares. So now you see those are the residual squares. If you take that vertical line right there, that negative, that's the square. If I move this, you can see that some of those squares are getting much bigger because the residual is getting longer, right? So the square is going to get bigger. If I try to minimize, so you can see it has the sum of squares there, 5, 5, 1, 3, 8. Ooh, that's pretty good. 5,600, that's not as good. 5, 0, 1, 4. So you try to get the, like right now, that's about the lowest I can get. Now I think there's better than that, but that's what I was able to get just by moving it around. So what you can do is you can go and we can actually undo this. So if you click on this line, but that's what residual squares are. That's what I want to show you right now. So let's do that. So one of the principles, determine if a linear model is appropriate. So in this case, we're going to use something a little different called residual plots. So residual plot is a different cat here. So it's a scatter plot that displays the residuals on a vertical axis. So it's not going to be slanted like it was. You can see kind of like, for example, this point at the very bottom there, there's a large residual there. This point on the bottom right is also that same point, but it's the vertical, the residual is actually vertical now. Instead of having to go up to a slanted line, you're going up to a straight line. But all the distances are the same. The residual distances are just pictured on an axis. So it just, you can't tell what the line is, but you can tell that the distance of the residuals is very easy to see. So let's try this. So let's go back to this. I'm just going to add a new data statistics page just to start over. Click sprint for explanatory and long for response. So this time I'm going to do something different. So I'm going to we're going to show the residual plot. So I'm going to do regression. So analyze regression. Usually we like the A plus BX linear. You could do MX plus B if you're more comfortable with that. And because I have my diagnostics on, it shows R squared. If you don't have that on, hit menu, 6 settings, and then click the diagnostics box. So my R squared is 0.7, which means, moderately strong. Seems like a pretty good description of that. So if we go to menu, analyze residuals, and now we choose, instead of show residual squares, which we never really use, we do use this residual plot. So now on the bottom, I have a residual plot of the same graph. It's kind of even vertically aligned. So you can see like that point on the left there is right on the line on both of them. That point, the second point on the left is pretty much on the line, it's just slightly above the line. This one, the third point from the left is below, it's also below there. So it's just kind of a vertical representation of this. And so that's what this residual plot is. Okay. So it magnifies the deviations from the regression line there. So it just shows, and so what you're looking for, if it's appropriate, the residual plot shows no obvious pattern. The residuals should be relatively small in size. So you like to see residuals that are smaller in size, that they're not super long here, points aren't super far away from the line. But what I like is it's kind of scattered. I see that as a lot of scatter. There's no obvious pattern. There's no curve there on the residual plot. They're just kind of scattered around. That means this data is a good linear fit. So you can actually tell by looking at the residual plot. So let me show you a few so you have an idea. If your residual plot looks like the one on the left, that is not going to be a good residual plot. In fact, that's the actual data there on the right that would cause this residual plot on the left. So if the data is curved and you're trying to fit a straight line to that data, it's going to have a curve in the residual plot, and you're going to see a pattern. It might not be as pronounced as this pattern is, but you will see it, and it will look like, oh, if there's a pattern, then it's not appropriate. So we want to look for scatter. No curve pattern in the residual plot. If that's the case, it's a good linear fit. If there is a curve pattern, it is not a good linear fit. You probably shouldn't be using linear regression. So here, does this look like a good fit for a linear fit, I should say. So it doesn't mean it's strong. It just means that linear is the right model to use. That's the right form to use. And so this one, I look at the residual plot, looks pretty scattered. There's no obvious pattern there. So I would say that this is a good linear fit for this data, that the linear is the right model to use here. Because there's no obvious pattern in the residual plot, the linear model is appropriate. If there was a pattern, I would say the linear model is not appropriate. How well does the line fit the data? And the role of S is the standard deviation of the residuals in this case. So we're talking about a specific kind of standard deviation. It's the standard deviation of the residuals. So the standard deviation of the residuals measures, we're kind of melding two things together. Remember, we think standard deviation is typical deviation from the mean. We think residuals are the measurement from the actual data values to the predicted data values, the y values, the predicted y values, the actual y values, that distance between the two. So we're marrying those two terms together. And so this is the typical distance, not deviation from the mean. It's typical deviation from the actual y values to the predicted y values is what we're talking about. So the distance or deviation from the actual y values to the predicted value typically. Okay, so we're kind of combining those two interpretations into one for S. R squared is called the coefficient of determination. So these are new terms. This is when you take correlation and square it. So if you create correlation and square it, it's always going to be a positive number. It measures the percent in the sum of the squared residuals using the least squared regression line. If you want to not copy this down, that's fine, because I have a script for you that you might rather copy down in your notes. I do like the last way it says it. In other words, R squared measures the percent of variability in the response variable that is accounted for by the least squares regression line. That actually is a pretty good definition there. That's pretty close to the script I chose. So I actually like the last part of that. The first part of that was a little cumbersome there. Okay. It tells us how much better the least squares regression line does at predicting values of y rather than simply guessing. So how much of that can be explained or predicted by the regression line? But okay. So in this one, we're talking about that same Ford Focus, that Ford truck. And so interpret the value of S. So think about S. S is the standard deviation of the residuals. The number there is given to us. It's $5,740. So the typical deviation or distance from the actual price of the truck to the predicted price of the truck is $5,740. That's the typical distance between the actual price and that. So interpret S. The actual price of Ford F-150 is typically about $5,740 away from the price predicted by the least squared regression line. The script you want to use, this is what I would say, instead of typical deviation from the mean, because this is standard deviation of the residuals, we would say it's typical deviation from the predicted response variable given a certain X variable, say that in context. So something like that would be fine. Again, you don't have to go exactly the same order. I'm not worried about that, but you kind of get the idea there of melding the definition of standard deviation and residuals together, because it's standard deviation of the residuals. R squared, we would say it this way: about 66% of the variability in the price of a Ford F-150 is accounted for or explained by the least squared regression line with, in this case, X equals a certain number of miles driven. And so that R squared value is 0.66. And so again, the script, you might want to write that down, something percent, about, some 66% or whatever the R squared value is. But the variation in the response variable can be explained or accounted for by the least squared regression line at a certain X variable. Talk about it in context. Okay, so now we have computer regression output. This first one's the one I see the most, but sometimes we see the other one. This is called Minitab. And so it's not labeled as nicely as we want. Some things are, some things aren't. So S is the standard deviation of the residuals. That kind of makes sense there. R squared, it says RSQ, which means R squared is R squared there. So that kind of makes sense. The other ones are not as obvious. So I've gotten used to, whenever I see coefficient above the word, I think, oh, that's the y-intercept. So actually the constant is what's to the left of it. So constant is what a y-intercept is. It's a constant, but it's in the coefficient column. And so that top one is going to be the y-intercept, and the bottom one in the coefficient column is the coefficient, which is the slope. And so the slope is going to be negative 0.16 in that case. Because you want to be able to look at this computer output and be able to come up with an equation of the line, like y equals 38.2257 minus 0.16292x. Of course, that's y hat, I should have said, and identify which one the standard deviation of the residuals is and which one R squared is. JUMP is set up in a similar fashion in that R squared is pretty nicely labeled. It says R squared as a number. S is not nicely labeled in this case for JUMP. This is root square mean error, evidently is the same thing as S, as the standard deviation of the residuals here. So that's what that is. I wouldn't have known that. Now it does nicely label the intercept is 38257. That's the y-intercept. The miles driven, this is not as obvious. That's going to be the slope, although kind of like the other form, the slope is right below the y-intercept. So if you can find the y-intercept, 38257, you should be able to find the slope right underneath it. So that's, both formats are set up kind of similar, but they're not labeled super nicely there for us. So we have to kind of get used to a computer output. We need to be able to write an equation from that if needed. So again, we did this a few minutes ago. We didn't write our answer in the proper form. So if we were to write our answer here, so I think if you can read that, that's our equation. So we would say, instead of y there, you would say y hat, which is our long jump distances. So you would say in parentheses, long jump distance with a hat over the top of it, a little tilde over the top thing over the top. So the predicted long jump distance equals 414.786 plus or minus, probably I just put minus 45.7433 times parentheses instead of x, I would put the sprint time or the dash time there in parentheses. The word sprint time or dash time would be fine to put there. Explains why the line calculated in part B is called the least squares regression line. Well, that's kind of what we were talking about, right? Because it minimizes the sum of squares, the regression squares. So let's see what the actual answer is listed here. Whoops. So it says the line calculated in part B is called the least squares regression line because this line makes the sum of the squares of the residuals as small as possible. It minimizes those sum of that. And again, I would not have defined these two variables. I would actually put long jump distance with a hat over the top in parentheses. And then instead of x, I would put dash time or sprint time in parentheses. So that'd be easier to do. Okay, so interpret per minute. Interpret the value of S in this context, right? So S is the standard deviation of the residuals. So the typical deviation of the actual value of a number of chirps per minute, that distance between that and the predicted number of chirps per minute is 0.97, right? That's the typical distance or deviation between those two things. Interpret the value of R squared. 69.7% of the variation in Y, which is number of chirps per minute, can be explained by the least square regression line when X equals some temperature, some given temperature. Okay. So again, when X equals temperature in degrees Fahrenheit. Those are the actual answers, and that's your lesson for today.